So this is me continuing with physical geography recapitulation. Now, interior of Earth. Basically, in the interior of Earth, there are two types of forces which cause changes on the Earth. One is endogenic force and exogenic force. So exogenic force is on the outside, whereas endogenic force is on the inside. Now, coming if we have to determine a few features of what the interior of the earth is, then there are two sources. One is direct source and one is indirect source. Before getting into that, one basic fact is that the radius of earth is 6370 kilometers. Okay, now under direct sources, it can be classified into two major into the following categories. First is mining projects. In mining projects in Africa, the deepest mines go to about 3 to 4 kilometers, and then there are two other projects called deep ocean drilling project or integrated ocean drilling project, and the deepest drill is at Kola, Arctic, which goes to about 12 kilometers. Then next we are another direct source about the interior of the earth would be volcanic eruptions. Okay, these volcanic eruptions bring forth the magma and lava which is on the interior of the earth to the surface. Next, indirect sources. Under indirect sources we have for the first one of the most important indirect source is meteors. These meteors basically fall on earth from outside. However, since they are found from the same solar system generally, or most, as also in most solar systems, as we have studied, the process of formation is the same. So since we cannot dig deeper into the earth, we can always rely on these meteors which fall on earth to study their internal structure and find out what would be the probable structure in the insides of the earth. Why we cannot drill into the earth? The reason is that temperature, density and pressure, all of them increase with depth, है ना? So after one point it becomes difficult to drill. Next, another thing we use another indirect source is gravitational anomaly. So basically earth is a geoid, and it is basically flattened at the poles, so the radius at the poles is less as compared to that of the equator, hence the gravity here is higher. So this is called a gravitational anomaly. And apart from these differences in radius, there can be differences in mass, density, composition, etc. And all of this, there can be many other factors. All of this will help us determine the interior of the earth. Another similar such thing which can be used is called the magnetic field of the earth. So magnetic field of the earth basically exists because of various ferromagnetic substances and which are rotating within the earth's surface. Okay, and this has resulted in the development of a magnetic field of earth's own surface. Okay, so this magnetic field of the earth, it has caused the magnetization of various substances on the earth. This is my understanding of what has been written on the NCERT as per internet and my limited to my understanding. Okay, and so we do something called magnetic surveys. So these magnetic surveys help determine the distribution of these magnetic substances through earth. Okay, so next comes earthquakes. So what are earthquakes? Earthquakes are basically disturbances within the earth's crust. When will an earthquake occur? An earthquake occurs when basically, see, there is a sharp release of energy along a fault. So basically fault is a sharp break in the crust, and they tend to move in the opposite directions. However, the rock, there is usually a large amount of rock strata which is overlying this fault or sharp break, and this rock strata exerts so much pressure that it is higher than the moving away tendency of these two plates. But sometimes this rock pressure becomes less. As a result, they slide. Okay, and this rock pressure basically leads to something called friction. Okay, if we go in detail, because of mu n, I guess. So this is weight and it creates friction. So under this friction, neither can this rock move forward nor can this rock move this way. But at one point, this friction will not be enough to prevent their tendency of moving away, and they will move away, leading to an earthquake. So the point inside the earth's crust where an earthquake emerges is called the hypocenter. Okay, and where it reaches the surface of the earth is called an epicenter. Okay, now we are going to talk about earthquake waves. Okay, so basically First, let us define the lithosphere of the earth. The lithosphere of the earth is up to a distance of 200 kilometers of the from the surface of the earth. Okay, so this will include some amount of crust plus asthenosphere. Okay, we will see in future what that is. So what happens is any disturbance here is basically recorded through a process called a seismograph. So these seismograph record earth waves or energy waves released during this process. There are basically two types of earthquake waves. One is a body wave and other is a surface wave. So body waves can further be of two types, P waves and S waves. And however, so now let us discuss the features of these waves first before going ahead. Okay, so first is P waves. P waves move faster. Okay, they are primary waves, high velocity longitudinal waves. Okay, and they can move through solid, liquid and gas. They behave similar to sound. But secondary waves, their velocity is less, they are transverse waves. Okay, and thus they can only move through solids. The surface waves, when they reach the earth's surface, they these waves, they will get converted into surface waves. These surface waves are much more destructive. Okay, and these earth waves also, since they're energy waves, they will definitely undergo reflection, refraction, everything, and that helps us determine the interior structure of the earth. We will see how. So basically there is something called a shadow zone. So basically whenever we are trying to measure the intensity of an earthquake, there are several seismographs that are planted various parts of the world. So if there is an earthquake here and there is this thing, so basically we observe that this is the kind of shadow wave, that shadow zone that we see. Shadow zone is the region where that wave is not being recorded. So this is 105, 105, this is 145, 145. So we know that S wave can travel only through solids. Okay, so as a result, this entirety is the shadow wave of, is the shadow zone of S wave, that is 105 to 105 degrees. However, in case of P waves, the shadow zone is 145 to 105 degree. This part P waves come. So this part, there is P wave visibility. This part, there is P wave visibility. This part, there is P wave visibility. Only this is the part between 105 to 145, which is the shadow zone for a P wave. Okay, so there is a drastic variance. So from this, what do we know? That the only reason why this particular S wave is not behaving the same way as P is because there is a fundamental difference. It can only pass through solids. From this we come to know that it is unable to cross the core. As you see, the wave has to cross the core to reach here. So since it is an S wave, it is unable to cross the core, and that is why the whole thing becomes the shadow zone of the S wave. And from this we know that it cannot be gas, obviously, under so much pressure. So we know that it is liquid. The outer core must be liquid, as we will see in the future. Okay, there are various types of earthquakes. Some of the major types that I'll be dealing with here are basically tectonic earthquakes. Okay, because of tectonic movement. Then volcanic earthquakes, very self-explanatory. Then there is collapse earthquakes, which occur in mines generally. Okay, intense mining activity. Then there is reservoir induced earthquake, because you build a huge reservoir, there is a lot of water pressure here. So this water pressure leads to development of cracks, faults and earthquakes. Okay, then the last thing that we have, so this is reservoir induced earthquake. Okay, and we have talked about that. Then there is explosion induced earthquake. So in case of an explosion induced earthquake, basically there can be nuclear device testing and chemical device testing, and all of that can lead to earthquake, obviously. Now measuring an earthquake, there can be two scales. Okay, one is measuring the magnitude of the earthquake, the other is measuring the intensity of the damage that is done by the earthquake. Okay, so this intensity of the earthquake is basically Mercalli scale. Okay, and it ranges from 1 to 12, whereas the magnitude is measured by the Richter scale, and it ranges from 0 to 10. Okay, next, effects of an earthquake, we know all of, there will be large amount of devastation and everything. One interesting thing is the formation of tsunamis. Okay, so tsunamis, basically there is an underwater foci, and as a result of that there is formation of these waves. Okay, and as the waves get closer, okay, these waves basically become more and more dangerous. They become higher and they become more dangerous because the width of the water column is decreasing, right? But that energy will be transmitted, so tsunamis become huge and they destroy everything on their face. This is again okay. Okay, now next we'll talk about the structure of earth. Okay, so if we are talking about the structure of earth, then so this is basically okay. So let's consider this the crust. If I do not get space, I'll make more. Okay, so let's first talk about the crust. So why have I drawn two crusts like this? First crust is basically the so basically there is a discontinuity here called Conrad's discontinuity. Now, what is this discontinuity between? It is between continental and oceanic crust. Now, continental crust at many places is just not there, you know, because so basically the universal thing that is below is the oceanic crust only, and it creates this kind of gap. This is called Conrad's. And what is the property? So we all know in case of continent convergence, the oceanic plate will always go down under the continental plate. So from this we know that continental plates are denser, okay, and continental plates are lighter and oceanic plates are denser, okay. So the minimum thickness of continental crust is around average thickness I'm talking about, not minimum, of continental crust. Okay, continental crust is 30 kilometers average thickness, and under Himalayas it is 70 kilometers. Okay, similarly oceanic crust average thickness is 5 kilometers. Okay, and so what is the density of the oceanic crust? The oceanic crust density, as we know, will be denser. It is around 3 to 3.3 grams per centimeter cube. Okay, and continental crust, we know it is less dense, so it will be around 2.7 grams per centimeter cube. Okay, now coming to the mantle. So we have seen that initially there was earth, now the outer layer is crust. So I am no more drawing the Conrad discontinuity. Now I am going to try to show you the Mohr's discontinuity. Okay, so Mohr's discontinuity will occur somewhere about here, so between the crust and the mantle. Okay, that was between two crusts. So this type of continuity was between two crusts. Okay, so if this is, so this would be Mohr's. This would be Mohr's discontinuity, and this Mohr's discontinuity marks the beginning of mantle. Now the property of mantle is that the initial 200 kilometers of the mantle now is very weak. This weak layer is called asthenosphere. So this asthenosphere is the source of all lava, magma, etc. It extends not initial 200 kilometers. My mistake. It is basically 400 kilometers. Okay, the depth, and so the mantle itself is divided into outer mantle and inner mantle. The outer mantle is made up of liquid, inner mantle is made up of solid, and the outer mantle, the end of the inner mantle is at 2900 kilometers. Okay, so the mantle extends up to a width of 2900 kilometers. Then the discontinuity that is present between the outer liquid mantle and inner solid mantle is known as rapidity. Okay, rapid discontinuity. So and the density of the mantle of the mantle is obviously higher than that of the crust, and the density of asthenosphere is just high. It's 3.4 grams per centimeter cube. Okay, that is why the crust is floating on the asthenosphere. The lithosphere on the other hand, so asthenosphere was up to 400 kilometers. Okay, so lithosphere is basically 10 to 200 kilometers. Now next we are talking about the core. So basically the mantle core boundary exists at about 5100 kilometers. Okay, sorry, 2000. Mantle core boundary exists about 2900 kilometers, as we have discussed earlier that the mantle is basically extending till 2900 kilometers. Okay, so when mantle core boundary is at 2900, the outer core begins from there. Then there is an inner core. The outer core is liquid, as we have discussed, which is why S wave cannot cross it, and the inner core is solid. So the outer core and the inner core is again separated. The mantle, so we have already talked about moho. Moho is between crust and mantle, okay, outer mantle. Then we have talked about repeti. Repeti is between outer mantle and inner mantle. Then there is Gutenberg. Gutenberg is between inner mantle and outer core. And then there is Lehmann. Lehmann is between outer core and inner core. Okay. तो 2900 किलोमीटर्स है एंड 2900 किलोमीटर से 5100 किलोमीटर्स तक जो है वो आउटर कोर है. Okay, the outer core is from 2900 to 5100, and as we know from the center of the earth will be from 6370 kilometers, since that's the radius. Okay, and the outer core is basically made up of the entire core is called a knife layer. Okay, it is made up of nickel and iron, and the density of material at the mantle core boundary means Gutenberg discontinuity, inner mantle and outer core. Here density is 5 and at the core it is 13. Okay, so to summarize all of this, the continental crust is 2.7, the oceanic crust is 3. Between them lies the Conrad discontinuity. Then there is the mantle is 3.4. Okay, this is outer mantle, it extends so 400 kilometers, we call it a asthenosphere, and this discontinuity is called Moho's discontinuity. Okay, and this Moho's discontinuity basically then there is inner mantle, this discontinuity is called Repeti. Then there is outer core, this continuity is called Gutenberg. Then there is inner core, this continuity is called Lehmann. This is the whole structure. Okay, 3.4, and we know that in the core, at the core mantle boundary it is 5, whereas at the center of the inner core it is 13. This is 5100 kilometers, this is 6370 kilometers. Okay, and this is 2900 kilometers, right? Yeah, so this is the net interior structure of the earth. Now let's talk about volcanoes. So basically volcanoes and volcanic landforms are a process of material which finds its way to the surface of the earth. Okay, an active volcano, if materials are being released or have been released in the recent past, then so basically all of this lava that finds itself to the surface of the earth is from the asthenosphere. This asthenosphere is the upper weak portion of the earth's mantle, and once the magma is inside, so basically when it is inside it's called magma. Once it has started traveling to the surface or has reached the surface, it's called lava. Okay, so what does it release? It releases nitrogen, S2, Cl2, argon and hydrogen. Yes. Okay, then next comes volcanic types. So volcanic types, the first that comes is shield volcano. So shield volcanoes are basically volcanoes like this. So these are very less steep, so there is high amount of flow, and these are basically basaltic. The lava is also basic, so it flows for a long duration. These are not highly explosive unless water gets into their vents. Okay, most famous example is that of Hawaiian volcano, and next they are characterized by low explosivity, as I told. And yeah, so basically all of this comes out as a fountain. Okay, it bubbles, it keeps bubbling at the top and leads to, and all of this bubbling and fountain like lava gets deposited here, and this results in the formation of what you call a cinder cone. Okay, now next comes composite volcanoes. So composite volcano are basically higher, steeper volcanoes at least. So these volcanoes, what happens is the magma that is coming out is acidic, Okay, so it basically deposits itself around the volcano in form of layers. That is known as the acidic. In layers. Okay. Along with lava, large quantities of pyroclastic material also come out. Okay. Then next comes caldera. Caldera is basically a volcanic activity in which so this is viscous lava. Obviously, they don't flow. Yeah. Next comes caldera. Caldera is very explosive, highly explosive. They are so explosive that they tend to collapse on themselves and cause craters called calderas. So this basically indicates the magma chamber is very close to that volcano. Obviously, that's why it's so explosive. Next comes flood basalt provinces. Okay, so flood basalt provinces are basically rivers of magma. So this magma keeps flowing in large basin systems. These are called flood basalt provinces, and the thickness care of this can be more than 50 meters. Okay, so Deccan traps which are present in Maharashtra are an example of flood basalt provinces. Then comes mid-oceanic ridges. We will see this later. In the mid-oceanic ridges, there is a 70,000 kilometer long mountain range which is present under the ocean. Okay, and the central part of this ridge system is basically a rift system and displays frequent volcanic activity. Okay, then next comes volcanic landforms. So basically volcanic landforms can be either intrusive or extrusive. Intrusive is that is they are formed within the earth's surface. Extrusive is on the surface of the earth. So extrusive are basically uh, the extrusive landforms are basically form of volcanic rocks. So these are rocks that have cooled down on the surface of the earth. Intrusive landforms are formed by plutonic rocks, and these are rocks which are cooling down in the interior of the earth. Okay, next comes okay, now we are going to talk about intrusive landforms. So under intrusive landforms, the first thing that we can discuss is called a batholith. So batholith are basically large magma chambers, and they are usually within the earth's surface. They become condensed and become form these large domes, and they are only exposed to the surface when all of this overlying material gets eroded. Okay, next this is called a batholith. Okay. Next comes laccolith. Laccoliths are basically composite volcanoes under the earth which are connected with a conduit to a magma chamber. So similarly, magma comes out. So this magma gets deposited around the volcano only, and it becomes a composite volcano-like structure. Okay, and they are found at deeper depths. Okay, next example is of both laccoliths and batholiths are Domal Hills of Karnataka. Okay, Domal Hills of KTK. Next comes laccolith हो गया. अब lapolith is basically saucer shaped. So under the earth this saucer shaped thing is taking place, and magma basically gets cooled like this. So this is known as lapolith. Okay, if at syncline and anticline this zigzag type thing takes place, it is called a phacolith. Okay, next is basically, yeah, this was a lapolith. Laccolith is the other composite one. This is laccolith. Okay, then bottom one is lapolith. Okay, and this is batholith. Yeah, and the next last thing that we are talking about is so we have talked about phacolith also. Phacolith is a zigzag thing. One thing is these also have a conduit below. Okay, these phacoliths also have a conduit. So two things, two places right now. So phacoliths and laccoliths have conduits. Okay, now there can be horizontal bodies also. Okay, if the horizontal bodies are thin, then they are known as sheets, and when they become thick, like sheet of paper, when they become thick, then they are known as sills, right? Obviously. Now dikes are perpendicular. So basically it is usually in case of flood basalt provinces, the magma was traveling like this, then it condenses to form this vertical or almost perpendicular like wall like structures. Okay, these are called dikes. They are again obviously, since Deccan traps are flood basalt provinces, they are common in Maharashtra, Western Maharashtra, they were considered feeders, okay, of Deccan tribes. Okay, thank you.